name's Anna May, and I'm a forester and the fourth generation of the Starker family. The Starker forest started in 1936 by my great-grandfather, T.J. Starker, and it's been in the family ever since. My grandfather, Bruce, and then my dad and uncle, Bart and Bond, and now me and my brother and a couple of my cousins are also involved with it. The Starker lecture series started as a way to honor TJ as well as Bruce, because they're both really interested in forums for debate and new ideas in forestry. After they both passed away, the family thought it'd be a good way to carry on their legacy.
Hello, my name is Klaus Puettmann. I'm a professor in the College of Forestry at Oregon State University. And first, I want to start by acknowledging that Oregon State University in Corvallis, Oregon, is located within the traditional homelands of the Marys River of Amnifo, sorry if I mispronounced that, band of Kayapua. Following the Willamette Valley Treaty of 1855, Kayapua people were forcibly removed to reservations in Western Oregon. Today, living descendants of these people are part of the Confederated Tribes of Grand Ronde Community of Oregon and the Confederate Tribes of the Siletz Indians. I want to welcome you to the Starker Lecture, the third in this year's session. The 2021 Starker Lecture series is titled Resilience in the Face of Disturbance, Learning from Disasters. It focuses on how communities, industries, and organizations across the forest landscape have responded to recent and previous disasters, shown resilience in the face of adversity, and are ready to play critical roles in creating a better future. Today's topic is research. We're going to ask questions like, how do we best study rare disturbances? What have we learned about disturbances in the past? And how can these research findings help us prepare future research studies, the forest, buildings, and society as a whole for future disturbances? I should mention that SAF credits will be available for this lecture. During the Q&A session, we will announce a keyword in the chat, so check for that. Please send your full resume, your full name, email address, and SAF or CF number along with the keyword, the email listed in the chat. After we hear from our speakers, we have 3 speakers, and they're going to give a presentation 20 minutes each. After we hear from our speakers, we'll have time for questions. So please feel free to submit your questions using the Q&A feature in Zoom. You can do that at any time during the lecture. So I'd like to introduce our first speaker, Dr. Fred Swanson. Since completing his PhD in geology at the University of Oregon, Fred, in 1872, Fred has studied geology-ecology interactions in both wild and managed forest landscape in the Pacific Northwest and beyond. The H.G. Andrews Experimental Forest and Mount St. Helens have been a focal point and other sites around the Pacific Rim. A central feature of his career has been to work at interfaces: geology, ecology, research, land management, biophysical, social sciences, and in the past 2 decades, also science, arts, and humanities interactions. Let's welcome Fred.
Thank you very much, Klaus, and thank you to the Starkers for making this lecture series possible. Good place to start is with this view, a drone image looking up the Mackenzie River towards the Three Sisters. The Holiday Farm fire started upriver there about 6 to 8 miles and blew violently downriver and incinerated the town of Blue River, which is at the bottom of this image. So we have both dramatic change in the forest landscape and in the human communities. More than 400 homes and many businesses were destroyed. The field of biophysical research of disturbances as it has advanced tremendously in the last few decades, especially with use of remote sensing and computer simulation modeling, technological approaches. And the social sciences have also evolved quite a bit in considering, for example, how social inequities affect people in disturbance zones such as this. But I'm going to, let's see, I'm not able to, oh, there we go. I'm going to drop back, and as an old-timey field scientist, I'm going to describe experiences from 4 events. The eruption of Mount St. Helens in 1980, the forest wars of the late 80s and early 90s, the 96 flood in this region, and the 2020 wildfires. And in each case, I'm going to talk about 5 topics. The first 3 listed here concern research, and I engaged in these places and in these situations as a researcher. And but I also got a sense for social consequences, precursors and consequences. And so the 2 points in blue are that larger social dimensions. Hence, I use the term big change events to encompass the human dimensions. So first, in terms of the common properties, is how our understanding of history can inform us about the likelihood of future events. The second point is during the events themselves or shortly thereafter, there can be aha moments when we learn things that influence our perceptions of these processes and shape our views of the science of them. And third, progressing through time, some of our research pertains to ecosystem responses and how they unfold over years and decades. In the human dimension, then, there can be dramatic changes in our thinking prompted by these disturbance events. And change is tough for humans. And our inherent conflicting values may come front and center in the context of these big change events. The first case then, Mount St. Helens. Here's a picture before 1980 eruption, the saint of symmetry, the Fuji of the Northwest. In the years before the eruption, 2 volcanologists of the US Geological Survey had spent a great deal of field time studying the eruptive history. Shown in the lower right corner is a pile of deposits from eruptions over the previous 10,000 years. There's a geologist there at the base of the outcrop on the left side of the insert. And they published a paper in 1978, at a time when the volcano had not erupted for 120 years. And they said they expected another eruption within a century and possibly before the end of that century. But then 2 years later, boom, Mount St. Helens erupted violently on May 18th, transforming the landscape viewed in the upper right corner, looking here north from the summit of St. Helens across Spirit Lake to Rainier in the distance, transforming that forested landscape to the one below. The cubic mile of the mountaintop peeled off and slid down the valley 12 miles, and a blast toppled the forest over 125 square miles in the middle ground here of this image. I had the interesting fortune to go to the site marked X in the lower right-hand panel on day 10, May 28th, 1980, with a couple other geologists. And I dug a small pit in the new deposits, and I saw dangling in the breeze particles of the former mountaintop, dangling from spiderweb-like filaments. I realized later that these filaments were actually fungal mycelia of burn site fungi, which had been triggered by the heat of the blast, although their adaptation to response to heat was an evolutionary consequence of the frequent forest fires in our region. These sorts of blasts are very infrequent and not of evolutionary consequence. So these fungal mycelia had ramified through these new deposits in the space of 10 days, and they were ready to sop up nutrients when the first rains came, which is their function out in the forest environment post-forest fire. So I got a couple points out of this. Number one, they're winners and losers in terms of biological response to any disturbance. And number two, it's important to think about the roles of the disturbance mechanisms, in this case heat, and not just the type of disturbance. I carried on after those early exposures and undertook some studies of the effects of different parts of the eruption landscape on erosion and revegetation. So here's a sequence of 4 images. The circle shows a helicopter for scale. This was about a site about 5 miles east of the volcano. It was a pre-eruption clear cut. You can see the stumps, you see the remaining poles from the young plantation forest that was present for the eruption. In the upper right corner, then you can see where gullies had been cut by the early fall rains. And then in the lower left corner, plants were coming up from the gully floors. Those gullies had cut down to the old soil surface and then stopped their incision. And the erosion then liberated plants to sprout from seed or rootstock. And this was an interesting aha moment in the sense that normally we think of erosion as a detrimental. And in this case, it actually accelerated ecological response. In the lower right panel, then we see the forest starting to fill in, but it still got a lot of gaps, and tree establishment was rather slow. So to summarize, these Mount St. Helens observations concerning history. The eruption history led to a prediction of the event. In terms of close-in observations, there are winners and losers. There was an immediate response of life, and then there's a story about the burn site fungi. In terms of ecological responses, it's been highly varied across the disturbance zones imposed by the different volcanic processes. And that ecological response has been relentless and protracted. Change in thinking. Wow, it can happen here, it can happen now, and we need to really accelerate our hazard assessment and monitoring. The U.S. Geological Survey's Volcano Hazards Program had its budget ramped up tenfold, and that included helping other countries who have volcanoes in a state of misbehavior. Venue for conflict. Should we go out there and restore the forest and freshwater environments, or let natural processes proceed substantially unimpeded? That was the language that was in the 1982 National Volcanic Monument Act, establishing a 110,000 acre monument centered on the volcano. But there were many points of conflict. You know, should we plant trees? Should we apply grass seed for erosion control? Should we stock fish and permit fishing in lakes within the monument, or let science study the natural processes? Going to the second case, the forest wars. And this is an image of old growth in the Andrews Experimental Forest up the Mackenzie Valley. And the Holiday Farm fire affected about 400 acres of the Andrews. This is a plot. You can see the aluminum tags and the 2 big old Doug firs here. And old growth and the northern spotted owl were the subjects of obscure research in the 1970s in the Andrews, but it became a focal point for the battle over the future forest practices on the federal lands within the range of the spotted owl. And so here's a legacy of a litany of the history of the timber era that developed after World War II in the Forest Service lands. And ultimately, Federal Judge Dwyer imposed an injunction stopping logging on the federal lands, particularly to deal with the declining population of northern spotted owls. And then President Clinton and Al Gore convened a summit in Portland in April of '93 to try to find a way to get relief from the injunction. A group of scientists gathered the week following the summit. And I happened to be in that group, and I had an aha moment in that context because there were 3 or so dozen scientists, specialists in all the relevant fields. And in the cubby holes where the river people and the salmon people were working, the GIS printout maps on their walls were all networks, stream networks, riparian zone networks with different buffer strip designs. And over across the way in the terrestrial ecologist world and the owl people's world, the maps on the walls were all patchworks of different age classes of forest, for example, good habitat or not so good habitat. And we did not have the conceptual framework as in the science community, in the landscape ecology community, to really put those two together. And that was an aha moment for me. And so I came back to Corvallis and working with colleagues here, we began a series of studies of how networks interacted with one another and with patchworks. So to summarize the forest wars conditions, first of all, the history of the progressive logging of the native forest under the timber era forest policy collided with directions for attention to ecosystems and other matters embodied in some of the federal legislation of the 70s. And other factors the history pointed towards inevitable big change coming. Close-in observations of concerns about interactions among networks and patchworks were key to understanding landscape connectivity and function, and therefore were needed in order to underpin how to design terrestrial and aquatic conservation strategies in concert with one another. The ecological responses have been striking. We could foster old growth forest attributes in the landscape, but still see the spotted owls decline due to various factors such as wildfire, disturbance of good habitat, invasion of the barred owls, and perhaps other factors. So this change was a big change in thinking with huge impacts on people. The old order collapsed and power shifted from the emphasis on timber production to ecosystem management. And here again, we had a venue for conflict over our values about forests. The '96 flood is the third case, along with some other folks in yellow raincoats there. I had the opportunity to hang out in the forest during the flood and see its progressive development over several days. It was fascinating as we could see the passage of the flood wave, the debris flows, the movement of large wood and boulders down through the landscape from the upper reaches of the watersheds and on down, ultimately to Portland. It was a big rain on snow event. Note the snow there. And so his work has been done on the history of floods and their origin as rain on snow events. And these are the events that make the big ones, but they're infrequent. We had the Christmas '64 flood, and then this '96 flood, and some earlier ones. We have some long-term stream flow records, indicating that they recur at intervals of multiple decades. The close-in observations were about how the disturbance processes cascade down through river networks and road networks, and how those roads and rivers interact with one another. We'd had some long-term observations of aquatic ecosystems in small and large streams, and we could observe the impressive ecological resilience of the aquatic system to disturbances such as this. We also had change in thinking, that notion of the roads interacting with the streams to influence the routing of water, sediment, and disturbances was a critical perspective. And then that came into play in the conflict venue, which was to find, how do we find the right balance between forest access and environmental hazards posed by roads, and how far to go in the name of watershed restoration with disconnecting road networks from stream networks. The fourth example is fires, the big fires, and the Holiday Farm fire of last fall. This is a view by Rob Much, who was a fire lookout at Carpenter Mountain in the Andrews. And this is a ground-based view at the mouth of Quartz Creek, looking north across the Mackenzie River in an area of industrial forest lands for the most part. So the picture for the wildfires of 2020. Starting in the 70s, we began studying fire history by counting tree rings on stumps in recently clear-cut areas, and transect of landscape scale site fire histories from Rainier to the Oregon Cascades, north to south and west to east, across the Coast Range and up the Mackenzie Valley to the High Cascades. We got a good picture that there was extensive wildfire in the period 400 to 500 years ago, and then again in the 1800s. Some of that 1800s period included the early European settler period. So wildfire in the wet west side has been infrequent, occurred at long intervals. Intervals as long as the main European settlement here. In the close-in observations, I've been going up the Mackenzie now to the fire zone about 15 times. Ecological legacies are appearing quickly, sprouting from forest understory plants and from the base of hardwoods. And carbon retention has been impressively high, but the amount varies greatly with the stock at the time of the fire. In terms of ecological responses here, these have been quite quick, but tree establishment will be slow relative to forestry standards. I do see cones that look like they contain viable seeds, cones high up in the trees. And so I think there will be some natural reseeding in a lot of these areas. But research on rate of Doug fir establishment in mature and old age classes indicate that it can proceed for more than 30 or 40 years. Change in thinking, again, it can happen here. Preparedness is helpful, but it goes only so far under extreme burn conditions, which we suffered in September. And again, this is a conflict venue, over surfacing our values of forests. And for example, how much salvage will be deemed appropriate in the course of logging of public lands. So some take-home lessons. Big change events may seem like surprises, and yet they're expectable. On-site observations can prompt science discovery. Ecological and human systems are quite resilient, but they may occur at inconvenient timescales. And there's plenty of need and capacity for new disturbance research, but the big challenges are human, are social. And expect uncomfortable change, and conflict. For just a moment to step back and ask what's next. What is the pace of big disturbances in our region? So here are 4 cases. Let's push your thinking back, to 70 years or so. We had the 62 Columbus Day windstorm. We had the 64 flood. We have the pandemic. So we've experienced one big change event per decade on average. And what might be the next big change event? Well, we've got plenty of candidates. We've got the familiar ones, big fires, but also ones we haven't experienced in our European occupation of the landscape, like big subduction zone earthquake and associated tsunami. So despite preparedness, our vulnerabilities may be increasing. There's concern about our infrastructure, communications, power and transportation. We've got difficulties on all those fronts, public health, building into more vulnerable spaces. All of these are points of concern. What next? Well, one thing may be community conversations. And in a way, these Starker lectures are a form of community conversation. And the OSU Forestry and Natural Resources Extension Program is about to begin some community conversations under the title, It Takes a Village. But they're tricky issues of sensitivity, of timing, as people are still in early stages of grief for some of the severe losses they have suffered. I would add one concluding point, and that is when conversations like this occur, let's bring the arts and the creative writing into the picture. I wanted to do that at Mount St. Helens in 1980 when it erupted, but I didn't get around to it for 20 years. And since then, we've had some interesting work on volcano arts and humanities. And we've also done work on fire, volcano, and humanities. And a bunch of this is in the context of the Spring Creek Project for Ideas, Nature, and the Written Word, in conjunction with the Andrews Experimental Forest Science Community and our long-term Ecological Reflections program. And part of the mission statement is to find new ways to understand and reimagine our relation with the natural world. This is in the words of Kathleen Dean Moore. So concerning fire arts and humanities, in 2012, with funding from the Joint Fire Sciences Program, there was funding to a group here at OSU and P&W station for a project on words on fire, wildfire, and literature. And there was joint funding to our colleagues up at University of Alaska Fairbanks. And they did a project on visual arts, the art of fire. And so both of these programs then explored how literature and art could be used in public communications concerning how we reimagine our relation with the natural world, including fire. And we had some really cool programs on volcano issues in Portland. And we have a book, In the Blast Zone, from OSU Press 2008 that captures a lot of the creative writing on reactions to the eruption and resilience of the landscape in the face of severe disturbance. So I thank you all for your attention. I look forward to some conversation later in the Q&A session.
Thank you. Thank you, Fred. What a great reflection. I guess something only somebody can do who's been there and ground zero, if you want to call it that, and who's at the same time be able to think about the larger question and put it in the broader perspective. So I should mention and remind you, we have the Q&A opportunity there using the Zoom Q&A feature. I haven't seen any question yet, but please, if you have a question for Fred, put it into the Q&A and we'll get to it later. Next, I want to introduce Dr. Kathleen Cavanagh. She's the Associate Dean of Research in the College of Forestry at Oregon State University, where she provides strategic leadership for an innovative, diverse, and widely respected research program. Previously, she was department head of the Ecosystem Science and Management Department at Texas A&M University, where where she provided direction and administrative oversight of 33 teaching, research, and extension faculty. Earlier, Dr. Cavanagh was on the faculty at the University of Idaho for 14 years, where she attracted $7 million of competitive research funds to study forest ecosystems. Her first academic appointment, however, was as an OSU extension forester in Clatsop and Tillamook County. Dr. Kavanagh attended Oregon State University, where she obtained her PhD in forest science after earning a BS and MS degrees in forestry from SUNY College of Environmental Science and Forestry, New York. Dr. Kavanagh is a forest scientist whose research contribution to our fundamental understanding of how forest ecosystems function and the assimilation of this knowledge into natural resource management. To date, she's published 53 research articles and delivered 73 national and international presentations. Dr. Kavanagh has more than 25 years of experience in teaching courses on silviculture, forest dynamics, and forest ecosystem analysis. In addition to formal coursework, she also delivered over 40 short courses for natural resource professionals on forest disturbance, fire effects, and forest regeneration. She's chaired and served on 39 graduate student committees, and she's been a member of multidisciplinary science teams to advise land management policy and continues to be an advocate for science and policy integration. Katie, take it from here.
Thank you very much. I find this is a really exciting time to be thinking about disturbance and the role of science in it. And I really appreciate the committee that put together these series of talks for coming up with the idea of resilience, and both in terms of economics and recreation, and now in terms of research. So it's been a nice series of talks, and I'm really excited to be part of it. And I also want to thank the Starker family for their support in the vision they provided in doing these lecture series. So my talk today is really about optimism meets reality, and how we plan and conduct long-term forest research knowing that disturbance is inevitable. Disturbance is not something we can ignore per se, but we know that it's inevitable. And it also comes in many forms, and we'll talk some about that as well, and kind of think about things both in terms of historic as well as current, and a little bit about the future, and also talk a little bit about the resilience of the research program at OSU. So to get started, I'm going to kind of also rely a little bit on the humanities, and from a quote from a philosopher that really struck me is this concept that Mother Nature is really the only major force, or one of our major forces, that's really totally independent of our will. We don't control Mother Nature in that terminology. We live within the confines of the natural system. We often refer to disturbances as natural disturbances, which indicates that we are recognizing that there is there's natural forces that we don't control. What we do is we respond to the disturbances, and it's really that response and how we think about them that is letting us think and get a lens into the future. So, and another thing that one of the things that Moshe Halbertal goes on to say is that if you try to control Mother Nature, or if you choose to ignore it, she'll slap you in the face, and that slap will be heard around the world. And I think we have a lot of examples of those. We often call it unintended consequences and a lot of other terminology, but typically we say often nature bats last. So whichever one of these parts of this philosophy or discussion you have, it's really important to recognize the context in which we are looking at disturbance and where we sit in the human nature part of it. So when you're conducting research in forests and you know that disturbance is inevitable, how do you, and this is where I was really hoping to do a poll, but I don't get to do that. But I'm really curious for you all to reflect a little bit on how you view disturbance when you're conducting research in forests. Do you think of, are you in the camp of fairly blissful ignorance? It won't happen here. Obviously this is a forest. Forests have been here forever, so therefore they will be here forever. And you kind of have this sense of blissful ignorance, and you think your study or whatever you're doing will not be impacted at all with disturbances, and you really don't plan for it. There's those that realize that disturbance is real, but they have the optimism or the hope that there won't be any disturbance over the time frame of the study that they're doing. And so they're hoping that there won't be any disturbance. And then there's this last category, and I would predict that this is where a lot of people are gonna fall into if I had done my poll. And those are the people that plan for and embrace disturbance as part of the system that they're working in, and recognize that it's those disturbances that have shaped the places that they're working in. And one of the people that I think do it better than anybody are really the entomologists and the pathologists that are out there. They're the ones that see the need and want for disturbance, and really embrace it, because the disturbance in terms of insects and disease is basically their bread and butter, and it's what they live for. So, oops. And so I think that, you can think about where you lie on the spectrum, and I'm going to be talking about some things similar to Fred, and in terms of disturbance and some of the lessons learned and the importance of big data and remote sensing, and also some of the human dimension, and a little less of the humanity. But I think that I agree with him totally that our response, our thinking about disturbance is really a systems-based conversation that needs to be had. So in terms of planning and embracing, many researchers go even further, and if you look at the multitude of disturbances, and these are the three that have happened to us since last September, and one of them obviously is the holiday farm fire. There's the massive, pretty bad windstorms we had over the summer or fall, can't remember anymore, it's COVID time. And then the ice storm that we recently had, that all had a fairly big impact. And in all the cases of these disturbances, we didn't get to control them, so to speak. We got to experience them. And the experience we had with them was really much a dependence of the scale and the location of where we were and where our resources are that we really cared about. If you were a forest landowner, you had tremendous impact maybe from the windstorm, but not so much from the ice storm, or vice versa. And if you are a forest landowner in the Coast Range, by and large, you escape these large fires, but you recognize that you're maybe next on the block. And so it's not something that you could totally ignore, but it was something that impacts us all, but in very different ways. Oops. Come on, you can go. All right, okay. But, and actually in research, we often go to great lengths to create a disturbance. And by creating a disturbance, we want to study it, and we want to study it in detail. And we don't have the patience necessarily to wait for that disturbance to do what we would want to do. So whether you are looking at the photograph of the burned over areas, that's just a site where they wanted to change the amount of ash that was deposited. And so they took from one area, they took all the ash off of it. They added it to another one. So one area got double ash. And the last one they left as just the ash that fell or was left after the fire. And so that's where we tried to change or create a disturbance. And the other one that you see here with the nice white stripes in it, that's a study in a loblolly pine forest in Oklahoma. And here they have used these troughs to intercept a certain percentage of the rainfall to cause a drought. So here you're trying to drought a forest to get the effect of that in without nature controlling that drought, but you're going to still, cause that drought to form on that forest. And these type of drought studies are very ubiquitous, and they go on all over the globe. And I think if you all think about it, you can think of many other instances where people have manipulated systems and go to create a disturbance. And if we were in person, I'd be asking for some of your input on that. So you've had a disturbance, and you've got to think to yourself as a researcher, what can you do following a disturbance? What's your response? And as Fred so aptly said, the response is to get there, to open up the senses and to be thinking about what it is that you can observe going on. And then the other part of it is we have these new tools in terms of remote sensing and a lot of other things that can help us see things from literally the 10,000 foot level. But how do you think about that in terms of research? And so if you think about who embraces conditions created during a disturbance, and a disturbance that many people don't think about that what relates to the natural environment is COVID and basically the shutting down of human movement through a big swaths of United States. And so there is a massive response that was quickly noticed when the national parks closed. And that was that all of a sudden bears were having parties in Yosemite, and we were seeing that, wildlife was thriving. And they were also seeing that there were wildlife, different species of wildlife in different parts of the parks. So the people that were managing the parks often stayed behind, and they said they'd see, whether it was pronghorn in a part of the park that they'd never seen pronghorn before, and they didn't realize was even pronghorn habitat. And so a lot of anecdotal thinking came out of that. And of course, you can imagine the people that had the luck and the foresight to have collared animals during this could have before and after type of records of how these animals moved. So it's kind of where the response and the technology could really align. And another case, and this is another human derived set of data, and don't dive into the detail on this data, but what this is, I'll just describe, is these are samples of mobile devices that we all carry on our phones and in our purses and in our pockets of people that opted in to have their movements recorded. And this is Yosemite National Park again, starts off in mid-September. And Yosemite was closed due to COVID for about 83 days, totally closed, so almost 2 months, and in the spring. And then it reopened, and then it closed again because of a windstorm. And so this is the beginning or the end of the second closure. And you can start to see the human behavior peaks during weekends, things like that. You can see a big peak around Thanksgiving, and you can see a small peak relative to the other times in December when people are on holiday. You can see that the 5 major areas of origin were San Francisco and down to lowest is San Diego, but they're all relatively local. You don't see the foreign visitors. You don't see people coming from long distances. And again, most of them were tourists, not local people, but they didn't come from very far. And that's, again, this is the kind of data that in a human dimension, thinking about a response to disturbance is really useful data, and one that again marries that technology, new technology, and our ability to track this data. And if you go to that website, you can actually choose lots of parks and actually look at the different responses. So it's kind of entertaining. And so I'm going to come back to a little bit, touch on kind of being prepared or ready to respond to fire in terms of research. And I'm going to use one of the same examples that Fred did, and that's the Holiday Farm fire. And the Holiday Farm fire, again, as you mentioned, burned into the H.J. Andrews for some time there was fear it was going to basically go up through the entire watershed and also take out the headquarters and all the buildings and labs. And this is probably one of the best instrumented forests in the world. And so while there was some trepidation of the instrumentation that was in there, there was also people saying, wow, maybe, you know, we'll see some change that we'll be able to follow over time as this system resets itself through a major disturbance. This shows you approximately, those of you who want to be oriented, that's the Blue River Reservoir. And I have flipped the map upside down so they're both oriented in the same way. So you can see the reservoir on the map and the reservoir in the photo. And then you can see the smoke columns that are coming. Those are small watersheds. And those are represented also in the map that you see here. And that is there's watershed 1 and watershed 2. And one of them is a second growth watershed that was logged, I believe, back in the 60s. And the other one is an old growth watershed that is basically a sentinel from the last major fire in this region. And so you have these two systems. They both had a fire. It wasn't as hot as the remainder, as the majority of the Holiday Farm fire. It was kind of near the end when the fire came into this drainage. And there was suppression worked fairly well, but there was still a nice burn in the understory, and that's represented here in this photo, this pair of photos, I should say, one of which is pre-fire with all the people there climbing. This is one of the sites where there's a lot of measurements going on, both in terms of water and atmosphere. And you can look up the slope across from behind this tower that you see the person climbing on, and you can see what that slope looks like now. So large changes, and kind of one of the interesting things is or I should say the H.J. Andrews and the researchers there have decades and decades of data on how this system behaved under a variety of weather conditions and storm conditions. And now they'll get some ideas and some measurements and collection on how it responds to this disturbance. Because again, this is heavily instrumented. There are plots all over through these watersheds. And so that assessment will be ongoing. And so it's almost the best of both worlds in this case, because the whole forest did not burn up. But at the same time, there was some fire that came into some key places that will allow us to study and understand more about the processes that go on when a fire does occur. Oops. Another site that we also is a really critical site was a site we have over in the Metolius region, and it's called an Ameriflux Site that's run by Bev Law and has been run for the last 20 years. And it was burned over around August 20th. So before the Holiday Farm and many of the fires that we saw on the west side, the east side was having its normal fire season. And this fire that came through here, one of the people that work up there sent me a message and basically said the damage is huge, very large loss. But at the same time, we see a multitude of research opportunities, and we look forward to that post-fire recovery science that will be able to be placed into context due to the 20 years of monitoring we have. And this site is especially important because it's measuring the carbon dioxide that's going into and out of the forests, which is a critical piece of knowledge we need today, and the response of that carbon dioxide uptake and loss and how it manifests itself in a site like this is a really critical piece of information. And one of the interesting things, if you look at this photo, it's kind of a before and after, is that the site here doesn't just measure the carbon dioxide uptake and loss from one part or one component of the ecosystem. It measures it over a very large area all around this ecosystem. And it's also coupled with other instruments that are measuring other parts, such as the soil and such as the stem respiration and also water fluxes. So it's giving us a picture of how this system functions and how that function and how things change in these cycles that are so important to us in the presence of a disturbance such as fire. So having this again, the synchronicity between instrumentation and disturbance can create some amazing insights into the future. So stay tuned on this one as well. And also, you know, having a fire that if it just had burned to this degree wouldn't necessarily be, I think, a full representation, particularly of fire in this ecosystem. But since we have a multitude of levels of fire in the footprint of this system, we also have the opportunity to think about things across levels of disturbance or intensity of fire. Oops, too far. Okay. So one of the things about the research that's been done, and I think Fred touched on this very nicely, is we have a lot of historical information. And a lot of the older historical information that we have is anecdotal. And this data from Morris, which was published in 1934 in the Oregon Historical Quarterly. And he basically tried to recreate what were some of the forest fires in Western Oregon and Washington. And one of the things that prompted this was kind of the initial Tillamook fire, one many people think of. And so using old newspaper accounts and the written record since the probably going back into the 1800s, was able to reconstruct some of the fires in an anecdotal form, gave some information about where the fire started, and talked a lot about the relationship between these fires and east winds, something we've all grown to see as an important part. And many people would take information like this and try to say, okay, well, if this is what happened then, this is our fire return interval, and therefore we can expect a fire. And they could look at their watch and say, in about 15 minutes or something. No, just joking there, but expecting, you know, thinking about when to expect a fire. When the reality is there's more nuance to that and more relationships. And one of them is, as we look into the future, and we look forward, is how much can we rely on the past? So if something is developed and it's anecdotal and we think we understand why and how, but we don't really have the data on it, we need to use the information that we're currently developing to help us project into the future. And that's where the data comes in. That's where the data becomes essential. And so in this case, this research group was looking at the forest vulnerability, and vulnerability is really defined as mortality in this study. And if you looked at the whole, at a very large scale of the whole Western United States, where were the most vulnerable fire-related systems, the most drought-related systems, and the combination of the two. And what, you know, you might think in terms of this large scale and relative vulnerability, the place you can expect mass mortality is maybe more in the south and a little bit less up in Oregon overall, unless you happen to hit that stochastic massive fire event like we did this last year. And so that's where the scale issue comes into play, and both in time and in space. So we've had to respond to to COVID also within our research community. And so how have we responded? And one of the things that we initially started was basically a shutting down of the system, and no travel, everybody go home. And then slowly we were able to rebuild to demonstrate we could travel safely. We could continue, especially to do our field research very safely. And so we were able to really have over 247 individuals be permitted to travel to go out and collect the data that was essential to keep the research enterprise going through COVID, and to collect some data that was essential in terms of the timing and the history of the record that we needed to capture. We also worked very hard in terms of research resilience to get our field, our indoor researchers going again, and trying to figure out the best way to do that in a safe manner. And so we went through a massive kind of assessment of research and what we could approve and what were the safety and COVID related changes we had to make. And so we had about 68 approved research resumption requests with 173 individuals. So again, much like the resilience of the natural system, we also saw a lot of resilience amongst the human system and amongst the research that we were conducting. So in closing, I'd like to say that we look forward to a future in forest research that does involve disturbance and that occurs at process level research that integrates disciplines, much like Fred talked about as well, that biological, physical, and social sciences really need to come together as we think about these things. We'll work across multiple scales from large wildlands, outdoors, and managed forests, all the way down to the sequencer lab, whether we're studying eDNA or tree improvement or whatever, we're working across multiple scales. And as we work in those scales from genes to soils to treetops in the built environment, they all face different disturbances, as we'll see in John's talk coming up. The built environment has one that also has some unique challenges and disturbances. And all these things will occur in the research we do in short and long time scales. We have experiments that are designed to last 800 years, much like the organism that we study. And in those studies, we can expect disturbance to occur. And really our role is to recognize it might occur and to figure out what our response is and how we'll be able to use that information for the betterment of our understanding so we can better predict what's going to happen as we move into a more novel future with climate change. So thank you very much, and I appreciate your attention and look forward to the discussions.
Okay, well, thank you, Katie. My name's John Nairn, and I'm the co-host with Klaus. And to remind the audience that they can submit question and answers directly with the Q&A tab, which the speakers can answer, can type responses, or time permitting, we'll have a Q&A session after the last speaker. So let me introduce our next speakers, John Vanderlint, who's currently the Harold H. Short Endowed Chair Professor in the Department of Civil and Environmental Engineering at Colorado State University. John has conducted nearly 50 research projects on buildings and other systems related to earthquakes, hurricanes, tsunamis, tornadoes, and floods. Between 2005 and 2013, he led projects that used the world's largest shake table to run tests on 2-story, 4-story, and 6-story wooden buildings. I think we're going to see some videos of those during his presentation. John serves on the American Society of Civil Engineers Executive Committee for the Infrastructure Resilience Division, and he's secretary of the Structural Engineering Institute Executive Committee. He's co-director for the Risk-Based Community Resilience Planning Center, headquartered in Colorado State University. This Center of Excellence is funded by National Institutes of Standards and Technology. It's a 14-university collaboration developing the computational resilience environment in core and engaging partner communities. John has published more than 400 technical articles and reports, including more than 200 journal papers, and serves on the editorial boards and a number of editorial boards, and editor-in-chief of the Journal of Structural Engineering. So I'll turn it over now to John for his presentation.
Well, thank you, John. And I'm delighted to be here as part of the Starker lecture series. First, I want to thank Katy for queuing this up. I found it interesting that your experiments last 800 years. Ours, as you'll see in a little bit, last about 40 to 50 seconds, but they take, sometimes feels like it takes 800 years to prepare for it. So today I'm going to talk to you primarily just about, you heard of the different hazards that we work on. I'm going to focus on a few earthquake engineering examples and talk about mass timber, or the application of utilizing wood products to achieve resilience at the building and eventually at the community level. So I want to rewind about 12 years to 2009. You heard about the world's largest shake table. This, to give you a sense of scale, this building is 10 stories tall. The door is 6 stories. And this table that you see on the right at E-Defense, it stands for Earth Defense in Miki, Japan, is about 50 by 65 feet, and it has a payload capacity of 2.4 million pounds. So the idea is, of course, to put a building on it and test that as if the ground is shaking. So here you can see this is a steel moment frame that's going to be used to lift it onto the table. You can see our interface, and I'll go through this kind of quick. I want to make sure we have some time for Q&A. So I think the photos can do it justice. Here we see this is what's called a stud pack at the end of a wall. And then we have, to take tension, we'll have a steel rods that go up the height of the building. Building will be 6 stories in this case. And the goal here was to design this as using a new method at the time. It was new, called performance-based seismic design. And that method enabled a certain level of performance for a certain intensity earthquake. And so here you get a feel for the lab up to 5 stories. And then this is test day. This is, there were a series of test days of smaller shakes. This is the big one, and this is the damage inspection crew that goes in, and we only have about 90 minutes to inspect the damage until we run again. So that's why the crew's so large, and I think I'm down there somewhere. And then this just gives a feel for some of the construction over time. So here's the shake. I'm going to start this just because there's a little lead time. You can hear them counting in Japanese. They'll then count down in the control room again while they check instrumentation. And so this building weighed about 800,000 pounds. It uses wood and wood products throughout, and then of course connectors, and it had more than 1 million nails. Give you a second just to reflect on the movement. And so it's fairly stiff, and that's what we want to see, some stiffness, but to get good performance, we don't want to see it displace too much for fear of collapse. However, when you get displacement, what happens is, this is up in the 6th story, and so this is just set up to look like someone's kitchen nook or kitchen corner. And this is about 35 feet up in the air. You can see people watching from a platform down here. They're far enough away. They look close, but they're not. And what happens is you get the stiffness, it increases the accelerations. And so now you're going to see what happens with acceleration. And so these are, to use Katy's words from earlier, these are these disturbances. We create them because we can't wait. We can't build a building and wait, years, decades, could be even longer to study earthquakes. So moving to resilience a little bit, if we think of the stages of resilience, here we have, you could think of this as functionality or whatever it is, but it's the community, it's whatever the goals of the community or for the building would be. But in the case of a community, we would have a hazard. This would be the earthquake, have damage. And what we're looking to do is we're looking to, of course, in structural engineering, always protect life, reduce or eliminate injury. And in doing that, we do that by reducing physical damage and maintaining the function or functionality of the building. And then what this does is it decreases the drop and allows the community to recover faster. And this is time on this axis. So now I want to move, fast forward from 2009 to 2013. The US has some very large shake tables too. The largest is in San Diego, California, at UC San Diego. It's a shared use facility. So we did a study there, and the goal of this study was to look at essentially what are called dangerous or at-risk buildings from a non-engineering terminology. And these are buildings, it says built prior to the 1970s, but many of these were built in the 20s and the 30s and the 40s in the Bay Area in California. And so a plan was put into place, and they identified that about 25% of these would be expected to collapse if there was a major earthquake on the Hayward Fault. And they do expect an earthquake on the Hayward Fault in the next 20 or 30 years. And of course, similar to Mount St. Helens, we can't predict exactly when. So this project, we looked at a number of different retrofits, had construction, testing, and I'll run through that in just a second. We used cross-laminated timber rocking walls as a retrofit. We partnered with a company, a corporation, to look at steel special moment frames just in the bottom story so the tenants wouldn't have to move out. These often are 4-story rental buildings. And then we looked at these more advanced performance-based methods. So we took what we learned in Japan and we brought it in so we could retrofit these, and looked at advanced technologies as well that you see here on the left, something known as viscous damping devices. And then ultimately, we took all the retrofits out and we performed a collapse test so that we could develop models and understand how these buildings collapse and how do you model collapse. And so just some quick construction photos. The steel is just an interface plate to get into the table and fasten it down. So that would be like your concrete foundation in your house. And these are soft story buildings, meaning this is a very soft and weak story. On this first story, you can see these huge garage openings, and the fact that there's really no stiffness in that bottom story to resist the motion. And so these are the buildings that we're trying to model. And in research, we can't pull one of those out and test it on a shake table. So we do as much as we can to reproduce that. And here you see our reproduction on the shake table to the right. So in the interest of research, as I mentioned, we had tested all the retrofits. We pulled those out, and then we looked at the collapse of the building. You'll hear a very enthusiastic research undergraduate student who's doing the filming here in a second. And he helped construct the building, so he was entitled to narrate, apparently. And so this is a very large ground motion. This is what's called a maximum credible earthquake. So this has a return period of 2,500 years. So we wouldn't expect this. We don't expect it to occur, but again, it's a return period. It could occur at any time. And so you can see here, this is barely hanging on. And so to study the collapse, again, we shake it one more time. So this is the damaged structure. We add mass throughout the building. There's steel plates all over, and that's so that it's representative of a real building, because it has floors, but it doesn't have furniture. It doesn't have a lot of things in it. And then these towers are just there to protect us, because you can see we need that. We're actually sitting right behind here in a 2-story building, so. And so essentially this 4-story building is there's an apartment in the bottom story, as well as that would have been the street direction, and it would have fallen out on the street, as you can see. And so as a reminder, we look at different retrofits to try and make these buildings safe, but also to make them resilient. And all of those were very successful. The shakes are interesting. They're not as fun to watch as the collapse test, though. So a project led by Shileng Pei at Colorado School of Mines that you see pictured up top here. And this has been a collaboration actually with Oregon State as well recently. And back in 2017, this is to look at post-tension cross-laminated timber rocking walls. So these are these massive walls. You can see just a 2-story version here that then go up the entire height of the building. Of course, they get spliced. And then steel rods are put in, and they're allowed to rock, and they dissipate the earthquake energy that way. And so this is a video that was professionally produced, as you can tell. And this was a 2-story test that was set up to try and try a proof of concept, because we are going to be testing next year. We'll be testing a 10-story building. And this is about a 2-minute video. I'll just play it as I try to narrate, since it's just music. And so you can see here various mass timber products going up, glue lambs, and they're laying in the floor system, which is cross-laminated timber. And this is going to be 2 stories. And there's also some bracing on here. Everything is set up as pins, so it's allowed to rotate. And then there was a composite. It was a composite design for 1 floor system. So you'll see some concrete overlay go in, a light concrete overlay on the first, and then on the actually on the roof level, excuse me. And then so here we see our panels going in. And this was led, actually, this floor system design and the floor was led by our colleague Andre Barbosa and Ari, that's I believe on as well, Senate at Oregon State. That was the collaborative part. And so here you see the concrete going in, and that's to get a composite action, and also for soundproofing or sound insulation. Now these holes you see here, this is where we're going to drop the panels in. So these are the post-tension rocking walls. Of course, they're not post-tension yet; they'll come in. And this is the control room that I mentioned where we were sitting. So in the other test, the towers were right here, keeping us safe. And so we've got one dropped in there. And they'll get coupled right here, mechanically coupled with steel, and that helps dissipate energy as well. In the 10-story test, of course, these will be put in 2 or 3-story sections and have to be actively spliced. Obviously, you can't drop a 112-foot panel in or 120-foot panel. And then these are put on, and the steel rods will come up, and these will be post-tension to dissipate the energy. And then steel plates added to bring us up to seismic mass. So I'll go ahead and jump forward. So here we can see this is a test. These should be synced, and here you'll see the wall. This is rocking. Here's the post-tensioning steel rods. And the students that have worked very hard on it back there watching. And you can see it taking all the ground motion energy and dissipating that. And that's, now the amazing part of this, we ran this twice. I'm gonna go ahead and show the other one. So this is the corner of that wall. And the idea is this is gonna rock. So this, you're looking over here. And here you can see it starting to lift. And the amazing part is that it's really not being damaged, and that's we're getting what's called 5% of drift, and that means 5% of the height, which is a huge drift. It's it's about 250% of what's allowed in typical design for buildings. And so what you notice is after 14 earthquakes, very large earthquakes in some cases, there's almost no damage to the cross-laminated timber rocking wall, meaning it's the whole system itself, thanks to the wall, is resilient. So the next step is a 10-story test. We're actually in a holding pattern waiting. They're upgrading that test that you saw, the shake table that you saw going in one direction. They're upgrading it so that it'll be 3-dimensional, it's fantastic, but of course we have to wait 18 months for that upgrade because it's quite an undertaking. So as I mentioned, then these resilient buildings, they protect loss of life. They reduce loss of life, or hopefully eliminate it, reduce injuries, prevent physical damage to the buildings, and improve the functionality of these. And so lastly, just a little bit more is one project that we worked on while some of this was going was putting cross-laminated timber into the U.S. design code. And I show this maybe a little bit just as for humor, but this is really the process to get something into a design code in the U.S. And I hope that clears it up for everyone. But but this is the process, and so we're fortunate that in the 2020 NIHR recommended seismic provisions, you can now see cross-laminated timber shear walls and cross-laminated timber shear walls with shear resistance provided by high aspect ratio panels. And so we have then the factors that will be needed for engineers to be able to design these efficiently and at a lower cost. And that's the goal, to enable the use of wood products in seismic design. So looking forward, just my closing views that mass timber buildings, they'll continue to get taller and taller, and certainly in the Pacific Northwest, where we're seeing a lot of mass timber activity and design, but also around the whole US. As you know better than anyone in this audience out there, the research and development is underway worldwide. The price points for mass timber right now, they're a little tall. I think they need to decrease into these large and 3- and 4-story, massive apartment complex projects. I'd really love to see that with tilt up and things like that. And then advanced technologies. You saw the viscous fluid dampers that we had. They worked great, but the advanced technologies, they have a place in enabling a lot of the mass timber projects and buildings around the US and around the world. But there is some work needed to move some of the theory into reality. And so I see a lot of those projects over the years going forward. And so I just want to acknowledge all sorts of people for the wood projects. And then with that, thank you for your kind attention, and I will yield the screen back for the Q&A. Thank you.
Well, thank you, John. As I was listening to your talk and seeing the videos, I did some tests myself, how quickly I can run from my office in Richards Hall to PD Hall in case of an earthquake. I still want to remind people, we still have the Q&A open. It's been a little slow. So I have a question I'd ask actually all 3 presenters in terms of how can we prepare to take full advantage of these disturbances, extreme events. And depending on your preference, how can a graduate student prepare, thinking about developing a research career? How can an organization like OSU, the College of Forestry, prepare? How can a landowner like Starker Forest prepare? And how can the general public, I guess, prepare itself, that we can take advantage of learning from those disturbances that we know will come? So maybe Fred, since you had the longest experience, I can put you on the spot. You start, and then the other 2 speakers can fill in.
Well, I don't have any silver bullet answer. It's interesting that the National Science Foundation began the long-term ecological research program in 1980. It's now on year 41, and there are 27, 28 sites around the US and some other places. And there was discussion of trying to be prepared to deal with disturbances. And, but I can't think of any way that we really did, except that when they have happened, that we pounced on it and have tried to capitalize. And when you've had 20 sites over 40 years, that's 800 site years of long-term observations. And you're going to have some big events, Luquillo in Puerto Rico with hurricanes, for example, they just got bam, bam, bam. So the key thing in terms of a research portfolio, I think of the nation and maybe a university community like ours here in Corvallis, is to be prepared to respond in an integrated way. And that may not be as much about what you can do in advance, but to have a culture of cooperation where you can capitalize on it when it does happen. It'll cause you to deflect some of your efforts, which you've traditionally where you've traditionally placed them. So I think maybe it's as much culture as anything else.
Katie?
Yeah, I guess I'd answer that question is basically to diversify. And that's to diversify both kind of particularly across space, that you don't put all your eggs in one basket if you can help it, whether you're doing research or whether you're, you know, if they, for example, Fred's example, if they put all the LTRs in Mackenzie River, you know, if they'd taken them, maybe put 5 in there or something like that, they would have all been lost into this one condition. And I think, so that's one of the take homes that I see from major disturbances. And the same thing, if you look at the large landowners, they have much more at risk. So the likelihood of them encountering a disturbance goes up because of just the broad spectrum of where their lands are. Small landowners are less likely to get impacted by a disturbance, but when they do, it's likely to be more impactful because they have a smaller scale to which they're working or managing under. So I guess I would definitely take that in the individual homeowner. I think you just have to be aware that it's not if a fire is going to occur, it's when a fire is going to occur. And do you have a good escape route? And do you have your emergency kit packed and ready to go? Because some of these fires aren't going to be controllable in the way that we've seen them in the past.
Thank you. John, you want to?
Yeah, thank you. You know, my answer is a little bit different given the subject matter, but I would say, you know, to me, affecting change and being ready for these events, at least, you know, the earthquakes and tornadoes and events like that, I think it requires us to start educating, at least within research, you know, these graduate level research programs, the new types of scientists and new types of engineers, and start to try and so this is maybe a more general answer, less focused on this, but to try and eliminate some of the silos and have somebody that maybe understands the whole process, you know, topically, and then they can drill down. And I think that comes back to, you know, a lot of what we do in academia. So kind of a general hand waving answer, but given the question and my subject at least.
Okay, you have another question that I want to direct to Katy as the Associate Dean for Research. It's really about we have different landowners, which offers different values, different management approaches on that. And what do you see as the research opportunities or activities showing up in terms of federal land and comparing, you know, salvage and fire impacts on federal versus private land on that? Do you see that on the horizon, or the activity proposals going in, funding opportunities, etc.?
Well, we've already, as far as I'm aware, we've gotten 2 NSF, what we call rapid grants. And that's when something happens and you want to get in there quickly to do some assessment and make some data. That's already come in. We have a cadre that was organized actually by Dean DeLuca, and actually, I would say, catalyzed by several of our faculty that work in fire. That's Kevin Bladen and Meg, and there's just a whole host of people. I can't name them all, sorry. But they started immediately working with this large group. And also we have this incredible force of extension faculty that just by happenstance, many of them were hired within literally weeks of the holiday fire and the other fires on the west face of the Cascades. And so we have together what I would call a cradle to grave group that are looking at the processes that are occurring, that are looking at some of the impacts, both and are also able to look at how to help people that are dealing with trying to make some of the decisions. So I'd say that we're well positioned, and I'd say that research is already underway. Whether or not it specifically addresses salvage logging, I'm going to have to defer to the scientists on that because I can't say for sure that's what they're addressing, but I can imagine that would be a component of interest to them in terms of the different types of treatments they want to observe.
Then there was a question, I think I'll direct it to Fred, but everybody else can obviously help out. So can you speak to the need for imaginative and creative thinking when it comes to forecasting feature surprises or disturbances? Especially how can we use our historical information to characterize plausible but novel future events?
Whoa.
West,
One thing that's been interesting to me is watershed memory. And I think we need, and also the charge that, history is dead. With climate change, is history dead? So I think we need to be very imaginative. We need to reflect on history and ask ourselves, how does the condition of the land, of the natural resources of the ecosystem, what are the consequences of different types and degrees of variation from the range of historic conditions? And for example, in the picture from the 96 flood, and there were some big logs there on the road, that very same site had also experienced about half a dozen big debris flows out of that experimental watershed, many of them originating at a road constructed in 1959. So at that very same site, there was a huge pile of old growth logs in 1964. In 1996, there was not a huge pile of logs, although the triggering events were very similar up in the source area. And that's because the channel had not reloaded. There was a memory of that earlier disturbance. So in some respects, it looked like a similar discharge event, but the consequences geophysically and ecologically were quite different. So we do need to be imaginative in thinking about how pending events may come to different consequences because of the biophysical and social conditions having changed.
And we have a question actually from our dean asking about our forest properties. The college owns forest properties and we're in discussion to maybe obtain more. And we know that we'll have some disturbances on our properties and we have a long-term research on those properties. So how do we integrate that into our research design, especially as we address long-term questions? So maybe Katie or Fred can give some hints.
This is something that we actually talk about quite a bit. And there's different avenues of doing that. One is that depends a lot on how much revenue you need from that forest to support your research enterprise. So many of our research forests, the revenue is used to support the research enterprise. And so so you would, in that case, you would need to have funds set aside to get you through a catastrophic loss or something like that. Or again, you would need to make sure you were diversified, that if you had forests in lots of different locations, the likelihood of them all burning up at once would be much lower than if you were concentrated on a single location. So I think that's another way to kind of keep a diversified portfolio, and also to manage thinking in terms of diversity of the ecosystem and to maintain those components in the ecosystem that are less fire prone. So whether it's hardwoods or in the coast and other parts, that you keep a fairly high hardwood component as well, because they're more likely to recover quickly as long as they're not consumed in a fire. So because they'll sprout, whereas a conifer won't. So I think it's, again, the answer is diversification and insurance.
So before we wrap up, I want to make a pitch. There's a new book from Bruce McCullough about uncertainty and risk, and then a blatant self-promotion. There's an article coming out in the Journal of Forestry soon dealing with extreme events. John, you want to wrap it up?
Okay, well, I thank all the speakers today, and to close out this 2021 Starker Lecture Series, we'd like to thank the Starker family, the Oregon Forestry Research Institute, and our College of Forestry for making this series possible. This year's series has been a 4-part panel series that has provided insight into difficulties of the past year in the areas of economics, recreation, education, and today was research. We've discussed issues we might face in the future and what can be done to ensure a better future for ourselves, our organizations, and our communities. If you want to see the lectures again or refer others to the series that might have missed it, all panel discussions were recorded and can be found on our website at forestry.oregonstate.edu/starker-lectures. We will not be holding a capstone event this year as previously advertised, which means this panel concludes this year's lecture series. Thank you for attending today. We hope to see you again in 2022, and hopefully the 2022 series will have more in-person events than we were able to do this year. Thank you.